Hi everyone, I hope you're okay and I hope that the videos will keep uploading and helping you out. On this video guys, we'll be talking about how does concentration influence the reaction rate. Please note that guys, each and every factor that affects the rate of reaction will have its own video because I just want to cover each factor fully. Are you together? On this video, I'm focusing on concentration only. Okay, we are told that learners used two experiments to investigate the influence of concentration on the reaction rate. They use magnesium ribbon and excess hydrochloric acid for the investigation. The balance equation for the reaction is given below. Okay, already we are told that our hydrochloric acid is in excess. That means the limiting reagent is our magnesium ribbon. Okay, we are told that for experiment 1, 5 grams of magnesium ribbon reacts with 0.1 moles per cubic decimeter of 50 moles of 50 cubic centimeters rather of hydrochloric acid, ne? And then for experiment 2, the same mass of magnesium ribbon and the same volume of the acid. The only difference is the concentration of our acid. Are you together? Okay, first question, they want us to use collision theory to explain the difference in the reaction rate between the two experiments. Okay, the reaction, the experiment rather that takes place whenever one of the reactants has the highest concentration will have a higher rate of reaction. So in this case, guys, I can simply predict according to collision theory that experiment 2 will have, or rather has, a higher rate of reaction. Has a higher reaction rate. Experiment 2, ne? Okay, now let's justify this statement of ours. Whenever, guys, we increase in concentration, okay, let me write an increase in concentration it increases the number of particles. Then, okay, or you can say the number of colliding particles per volume. Right, together, it increases the number of colliding particles inside the reaction vessel, and hence now we'll end up having more, or rather, let's say the number of effective collisions, will increase. It increases per unit time. Right, together, and then hence we have the rate of reaction also increases. Right, together. So in experiment 2, guys, we have a higher concentration. Right, together. So this higher concentration will just increase the number of colliding particles inside the reaction vessel. Excuse me. And then whenever the number of colliding particles increases, we'll end up having more effective collisions per unit time, and that's why we'll end up having our rate of reaction to be higher. Are you together? Okay, now let's go to the second question. The sketch below illustrates the Maxwell-Boltzmann distribution curve for both experiments. Which curve between P and Q represent experiment 2? Remember that, guys, experiment 2 is the one that was held at a higher temperature. Are you together? So the one that was held at a higher temperature, it will have a greater peak than the other. Are you together? Remember that, guys, the basic Maxwell-Boltzmann distribution curve is simply like this. And then obviously you'll have your average kinetic energy, your activation energy over there, ne? And let's say now experiment number 2 takes place at a higher temperature. That means your graph will just spike a bit there. and then progresses like that, né? But if the reaction took place at a lower temperature, it was just going to be like this over here. Are you together? So now I know that, okay, graph Q represents the experiment with the highest concentration because it has a higher peak. Are you together? So graph Q is the one that represents experiment 2, né? Okay, and then now we are told that the graphs below, rather the sketch below is the representation of the formation of hydrogen gas over time. Which curve represent experiment 1? We have two curves over there. There's curve X and curve Y. The curve that reaches completion faster will represent the experiment with the higher rate of reaction, and the curve that will reach completion later on will represent the experiment with the lowest concentration, né? So in this case, curve X reaches completion after 300 seconds, because you can see that after 300 seconds we simply have a flat line over there, né? Are we together? And then and then guys, for curve Y, the reaction reaches completion after 500 seconds. Are you together? Because that's when the curve starts to be straight over there. Are you together? So the one that reaches completion later, that simply means the one that has the slowest rate, or rather the lowest rate of reaction, né? In this case, we have established that experiment 2 have a higher reaction rate, but experiment 1 will simply have a lower reaction rate, né? So I now know that, okay, curve Y represent experiment 1. Are you together? Okay, and then now we are told that if both experiments took place at 40 degrees, at completion the volume of, or another thing, guys, that's I want us to note, né? If, guys, we increased the concentration of our limiting reagent, we would have our graph to have a greater outcome of products. Are you together? But since we have increased the number of the concentration of our reagent in excess, it simply means that in both experiments we will get the same products, the same amount of products. However, it will take it will take more time to form the products in experiment 1 than it will in experiment 2. Are you together? Okay, now we are told that if both experiments took place at 40 degrees Celsius, at completion the volume of hydrogen gas was 540 cubic centimeters, and then at 40 degrees Celsius we are told that the 1 mole of a gas occupies 27,000 cubic centimeters. They want us to calculate the rate of reaction in grams per second in experiment 1. Okay, I'm given the volume of a gas that was collected, né? I can simply find the number of moles of my hydrogen gas. The number of moles of my hydrogen gas is basically equals to the actual volume of the hydrogen divided by the molar volume of a gas, né? That's 0. Please make sure that, guys, whenever you use this equation, make sure that your volume is always in cubic decimeters, né? So you just take whatever volume you have in cubic centimeters, divide it by 1,000. You'll end up getting 0.54 divided by 27. 0.54 divided by 27, 0.54. So this will give me 0.02 moles. Are you together? This will give me 0.02 moles, né? So I want to calculate the rate of reaction in grams per second. Remember that, guys, by definition, rate of reaction is basically the change in quantity of products over the given time, né? In this case, the change in quantity of products we're talking about the change in mass of our products per unit time. How do I know that? Because I was told that the reaction rate must be in grams per second. Are we together? In grams per second. Okay, for me to calculate the reaction rate, I must simply calculate the mass of my hydrogen that was formed. I know the number of moles of my hydrogen that were formed. I can therefore simply go and calculate the mass of my hydrogen. How can I find the mass of my hydrogen? I'll simply say number of moles is equal to mass of my hydrogen divided by the molar mass. Divided by the molar mass. Né? I have 0.02 is equal to the mass of my hydrogen divided by 1. So therefore the mass of my hydrogen is just 0.02 grams. This is the mass that was formed of hydrogen. Eh? So our rate of reaction will be equal to the final mass minus the initial mass. Initially, when the reaction progressed, there was no hydrogen present in the reaction vessel. Eh? So that's why I'm subtracting 0 grams of hydrogen all over time. It took 500 seconds for experiment 1 to reach completion. So I'll simply divide by 500. So whenever I do so, I'll simply get an answer of 0.0004. It's 4 zeros actually. 0.04 grams per second. Né? Or you can simply say, if ever your calculation, if ever your calculator is in scientific mode, that's 4 times 10 to the power 1, 2, 3, 4, 5 to the power negative 5 grams per second. That's how, guys, we're supposed to calculate this rate of reaction, and this is how, guys, you deal with the influence of concentration in the reaction rate. Né? And we obviously predict our reaction rate by simply using collision theory. Are we together? This was the most important part of this video. However, I know that these questions are normally asked, and they are also worth your time because they cost you 5 to 6 marks. So it's very important for you to know these questions. Né? Since we were given the volume, the first thing we did was to find the number of moles of our gas. Secondly, we calculated the mass of our gas, since the rate of reaction should be measured in grams per second. Thirdly, we calculated the rate of reaction because now we know the amount of mass that was formed of our hydrogen gas. And then we found our reaction rate. That's how, guys, we deal with reaction rates. On this video, I was focusing on concentration. Just know that the other videos, guys, are already uploaded. Né? So just stay tuned and wait for more. Thank you.